Welcome to my channel. Today in this session, let us discuss about the synchronous decade counter. Already we have discussed about the synchronous counter. Today let us see about the synchronous decade counter. So by the name itself, we will know that it is able to count from the states 0 to 9 since the name is given as the decade counter. Okay, so synchronous BCD decade counter is shown in figure, right? This is the figure which says about the decade counter, right? So let us see the operation sequence diagram and also the timing diagram. Since it counts from the 0 to 9 decimal numbers, that means 0 to 9 states. For 0 to 9, it will have 4 bits. So in order to count the 4 bits, we have 4 flip-flops, right? Synchronous counter is different from asynchronous counter only by the means of the clock pulse, right? Here in each and every flip-flop we provide an clock pulse, and but in the asynchronous counter and single pulse is given to one flip-flop, and the output of the first flip-flop is given as the clock to the second flip-flop. This is the main difference between the synchronous and the asynchronous counter, right? Coming to our discussion here, for the designing the synchronous counter, there are four flip-flops: flip-flop A, B, C, and D, right? Initially, the clock pulse is given to the flip-flop A and then to B and C and D. Separate clock pulses are given, right? And also the inputs of J and K, here we have used to design the flip-flop by the means of JK flip-flop. J and K are connected to high. That means only in the case of high state, the JK flip-flop tends to toggle. That means changes its state, right? The output of JK is ANDed with the AND gate and it is given as the input of JB. And here also the JB is provided by flip-flop B is provided by its own clock pulse, and each and every flip-flop it is ANDed with the AND gate, and the finally the output is given to the fourth flip, right? This is the simple operation of the synchronous decade counter. And coming session, let us discuss how it toggles and changes its state and how the AND operation is happen, and the and by the AND operation how it changes its state, right? Let us examine. So initially, as discussed earlier, the flip-flop A toggles on each clock pulse. That means the pulse provided here. So the logic equation for its J and K inputs are JA is equal to AA is equal to 1. For this logic, automatically it toggles. That means it changes its state, right? So this is implemented by connecting these inputs to a constant high level. That means when both J and K of flip-flop A is connected to high, there will be a change of state for the provided clock pulse. Okay, this is the first operation in the case of this counter. And next is for the next clock pulse, each time when QA is equal to 1 and QD is equal to 0, this is the output of the fourth flip-flop, and so the logic for its J and K input will be QA equal to QD bar. For the second flip-flop, the logic equation will be this, and the input will for the flip-flop B will be QA is equal to 1, high input, and the output from the last flip-flop will be 0, right? This is done. This logic equation is obtained by implementing ANDing and gate QA and QD bar and connecting the gate output to the J and K flip-flop inputs to flip-flop B. That means in the logic circuit diagram, this operation is done. So the output of flip-flop D is given as the input to the Q flip-flop B. Here QA is equal to 1, and since it is knotted, here QD bar is equal to 0. So this is the logic. Since we are providing the input towards the AND gate, we have QA into QD bar, bar. This is the logic equation for the flip-flop B, and for this logic it has a change for the provided clock pulse, right? And for the next flip-flop, the flip-flop C changes on the next clock pulse for both QA is equal to 1 and QB is equal to 1. So for this logic, it changes this state. This requires an input logic that Q, J and K which is equal to QA and QB, right? Initially, JA is equal to KA is equal to 1. This is the condition. And next, JA is equal to 1 and JB is equal to 1 and KB is equal to QA, QD bar. That means QA is equal to 1 and QD bar is equal to 0. And for the next condition, JC is equal to KZ is equal to QA and QB. For this case, both QA and QB are high, so it has a change of state. So this is also implemented by the means of ANDing QA and QB by connecting the gate output towards the JK flip-flop. So this is given in the circuit. For the flip-flop C, QA output is high and QA A output is also high. QB output is also high. The output from the AND gate is nothing but QA, QB, which is given as the input for the flip-flop C, and the flip-flop C changes it straight, right? Q flip-flop A is at high and flip-flop B is at low, and once again flip-flop C is at high, right? And the next case, next is, so for the each and every clock pulse, the flip-flop changes its own state, and finally for the next clock pulse, the flip-flop D changes to the opposite state on the next clock pulse when QA, QB and QZ is equal to 1 or QA and QD is equal to 1. For this logic, automatically the flip-flop D changes its state, right? So this change of state is implemented by the AND OR logic for the flip-flop D, right? And sequence of states which the synchronous counter counts is from 0 to 1, 2, 3, 4, 5, 6, 7, 8 and 9. So these are the states that which count for the provided clock pulse, right? For the initial clock pulse, all the states are 0, and for 1, the change of state QA will be high. That means for for the flip-flop A, when both the inputs QA and QB are connected to high, the QA output will be high. And next, for the second clock pulse, the QA output will be 0 and QB output will be high. For the next clock pulse, QA output remains in its own state and QB also remains in own state. QC changes its state with the logic equation which we have discussed, right? So, for the fourth flip-flop, sorry, for the fourth the pulse, QC changes its state, and for the fifth pulse, QA and QC remains the same. QB changes its state from 0. So for the sixth, there is a change in QC and there is a change in QB, and the seventh, there is a change in QA. 8, there is a change in QD. And once again, after this pulse, the flip-flop resets and start counting from the initial state, right? From 0. Okay. So this is made by the operation having the flip-flop state inputs J and K to be high. When the initial the flip-flop input is high, it toggles the next state depending upon the clock pulse. So this is given in the means of the timing diagram. So in the timing diagram, this is the clock pulse which we have taken, right? So the pulse 1, 2, 3, 4, 5, 6, 7, 8, and 9, 10, the pulses which tends to count. And as discussed earlier, initially QA output is given and QB output is given here, and the QC output and the QD output. For each of the trailing edge, automatically it changes its shape from high to low, right? So flip-flop A, for the after the first clock pulse, it changes its state from high to low, and flip-flop B, after the first clock pulse, it changes its state from low to high, and similarly flip-flop C, it starts to counting for after the third clock pulse, right? For after third clock pulse, it changes its state from low to high, and QD, it changes its state from low to high after the seventh clock pulse. So this is given in the case of the sequence also. As explained earlier, for first clock itself, QA changes its state, and for QB, it changes its state after the third clock pulse. So QB changes its state after the third clock pulse, and after the seventh pulse and at the eighth pulse it changes QD, changes its state. Similarly QC changes its state after the third, and it starts to change its state at fourth pulse. So here at the fourth pulse QC changes its state, right? So this change of state is happened by the means of initially connecting the flip-flop JA and KA towards the high input, and the output of the first flip-flop is fed as the input to the second flip-flop with the AND gate. So ANDing the input with the AND gate, we have a change of state from low to high and also high to low, right? So this change of state toggles the next state depending upon the clock pulse, and with this the BCD counter or the decade counter counts the state from 0 to 9. Since it is a BCD counter, binary decoded counter, it counts the states from 0 to 9, right? So with this discussion, I stop here, and if you like this video, like, share and subscribe.